All right, thank you all for coming back promptly from lunch. My name is William Huggins, and it's my pleasure to introduce Oskar Leimkuhler, who's going to tell us about barriers to dequantization of near-term molecular electronic structure methods. Take it away, Oskar.
Great. Hi, everyone. It's great to be here. So today I'm going to be talking to you about our recent work, which I will cover the main results of in the last part of the talk. So this is going to be a talk about what we could call quantum heuristic methods for molecular electronic structure, and it's also going to be a talk about complexity theory. So I'm going to split the talk into two parts. In the first part, I'm going to try and motivate an ansatz for quantum chemical wave functions, in particular ground states, and then in the second part of the talk, I'm going to see how far can we get towards proving that there is a barrier to dequantization under complexity theoretic assumptions. So just to reiterate, so our question is, can we find a useful wave function ansatz for molecular electronic structure that produces expectation value estimates to some constant additive error using a quantum algorithm that has a provable barrier to dequantization under complexity theoretic assumptions. So we're going to see how far we can get towards answering this question in this talk. So I can assume that we're all happy with the clamp nuclei and finite basis approximations for molecular electronic structure, and also second quantization. So we have fermionic operators that are linear combinations of strings of creation and annihilation operators, and our Fock space is spanned by Slater determinants of fixed particle number. So if we diagonalize in the space of all Slater determinants, then we get, for our purposes, the true ground state energy, which is within the bounds of the approximations that we've already made. That is clamp nuclei finite basis. And we're going to use this very limited definition for the molecular electronic ground state problem, which is that under these stated assumptions, we want to compute an energy estimate that is within a constant additive error of the FCI energy. So there could be cases where a relative error that depends on the size of the system is a more appropriate appropriate target, but there will also be cases where a constant additive error is the better target. So we are going to focus on this. In particular, we want to target the, rather than just looking for a sort of generic quantum speedup in quantum chemical calculations, we're going to target the particular systems that are the most challenging for classical methods, such as the strongly correlated active sites of certain biological enzymes. These are some common examples that people are interested in, like the active site of the oxygen evolving complex of photosystem 2 is important to understand photosynthesis, and the iron molybdenum cofactor of nitrogenase is also one that is talked about a lot and is key to understanding nitrogen fixation in bacteria. So full configuration interaction scales exponentially with the size of the size of the system, which in a sort of moderately descriptive basis set, we find We find estimates for the number of Slater determinants that we would need for a brute force FCI calculation that are just astronomically large. So 10 to the 70 for the active site of the oxygen evolving complex, and 10 to the 136 for the iron molybdenum co-factor. So we are going to replace the FCI wave function with a best guess, what we call an ansatz, which this is the sort of this is the heuristic part in quantum heuristics, and we would like this to be variational and size consistent. I'm also going to assume that we're all happy with the Jordan-Wigner transformation, which is how we're going to decompose fermionic operators into Pauli strings, and also define fermionic quantum circuits, such as UCCSD. So coming back to our central question, can we find a useful quantum ansatz for molecular electronic structure, for which we have an efficient quantum algorithm to compute these energy estimates to a constant additive error that also has a provable barrier to dequantization by any classical algorithm. So in the remainder of this part of the talk, I'm going to try and motivate a particular ansatz and explain why this could be useful for molecular electronic structure. First, a quick refresher on orbital rotations. This is going to be a sort of central object for the remainder of the talk. So an orbital rotation is a unitary transformation of the single particle basis. In second quantization, it can also be written as a unitary transformation of the creation and annihilation operators. You can also think about this as a Bogel-Yubov transformation, which conserves particle number, so it prepares a subset of fermionic Gaussian states. And these are also equivalent to one-body dynamical evolution. So that is time evolution under a one-body or quadratic fermionic Hamiltonian. So if you have some Slater determinant in one basis, then an orbital rotation transforms that into a Slater determinant in a different particle in a different single particle basis. And the overlap between the rotated Slater determinants is efficiently computable. We can also efficiently express the Hamiltonian in any orbital basis, and it's well known that the choice of orbital basis can significantly affect the computational hardness of any subsequent ab initio calculation. So typical choices for classical methods are mean field or spatially localized orbitals. Okay, so I'm going to briefly cover some qualitative features of molecular electronic ground states, which are well known within quantum chemistry, but are less widely circulated in the quantum algorithms community. So the first question that we can ask about what the ground state wave function looks like in some sense is it smooth or does it have sharp cusps? So in other words, at points in configuration space away from the nuclear centers, is it smooth or are there discontinuous first derivatives? And it's very easy to see that at all points in configuration space where two electrons with opposite spins have the same spatial location, you have these sharp cusps in the exact wave function. If you think about your single particle basis, so that consists of smooth wave functions at all points away from the nuclear centers. And that means that you are trying to approximate a sharp function with a linear combination of smooth functions. And what this translates into in practice is that when you have an expansion for the wave function in terms of Slater determinants, you have these long tails which reach up into the highly excited determinants. And this is a feature which we refer to as short range dynamic correlation. So one important thing to point out here is that this flat line here is a Hartree-Fock solution. So in other words, a single Slater determinant. And we have seen that Slater determinants are prepared by orbital rotations, which are related to one-body fermionic evolution. But this dynamical correlation effect is fundamentally a two-particle effect. So what that means is that it is not possible to capture the dynamical correlation with a rotation of the orbital basis. So in other words, there is no orbital basis that gives you the dynamical correlation. You always need to include two-body interactions into the wave function description. On top of this, in the most challenging systems for molecular electronic structure methods, we also run into a phenomenon known as static correlation. And one way to understand what is going on here is that when you have many near degenerate molecular orbitals, the valence electrons, that is the electrons that participate in bonding, they can delocalize over this space of near degenerate orbitals, and this the consequence of this is that the ground state wave function is not even perturbatively close to any single Slater determinant. In such, so one very common example that people talk about is half-filled D subshells of transition metal complexes, and another is stretched bonds or bond breaking. This is a sort of very general feature of when you stretch bonds. And this is often well treated by a linear combination of Slater determinants in rotated orbitals. So not any single Slater determinant, but a linear combination. And they're in non-orthogonal orbital bases. So now you may be wondering, well, if these are the qualitative features of molecular electronic ground states that we want to try and capture with an ansatz, then why don't we just add perturbative corrections for the dynamical correlation on top of a base wave function which captures the static correlation. And this is exactly the point. This turns out to be very non-trivial for classical methods. And it's exactly this gap in the market which the non-orthogonal multi-reference ansatz is specifically designed to target. So the basic idea is that the wave function ansatz is a linear combination of correlated reference states expressed in different orbital bases. So as a hybrid quantum classical method, this comes under the umbrella of what you could call, what are often called quantum subspace methods, which compute these off-diagonal Hamiltonian and overlap matrix elements on a quantum computer and then solve a generalized eigenvalue problem on a classical computer to extract to extract the energy estimate. But I should point out that this is distinct from quantum Krylov methods, where there you would use real or imaginary time evolution for the reference states, but we're not basing the choice of reference state on that. So the key source of I just want to really emphasize that the key source of quantum what we need the quantum computer for is this Hadamard test circuit. So this is what we can base our claims of quantum advantage on. That dequantizing this quantum circuit here has some kind of barrier. So this gives us a framework to extract energy estimates, and this is quantum efficient, provided that the following conditions hold. So that the one norm of the one norm of the Hamiltonian, the number of reference states, the circuit depth of each reference state, and the condition number of the subspace all grow polynomially in the size of the system. Now this is a part that we often get a lot of questions about. In particular, what kind of intuitions should we have about how the number of reference states will grow with the system size? And I'll be happy to answer questions about this at the end. The short answer is that it very much depends on the choice of reference states and how you construct the subspace. So one idea that we have had is to use unitary coupled cluster doubles within each orbital basis to treat the dynamic correlation, and then use the linear combination of reference states in different orbital bases to get the static correlation. So we can use existing classical methods to find both the two body amplitudes and the orbital bases, so not needing any hybrid quantum classical optimization. And we tested this out on H2 and square planar H4 with encouraging results. Another idea that we have had is to use matrix product states as the reference states. So this primarily targets the static correlation in the hardest possible active spaces. So where you don't have a one-dimensional area law of entanglement, so DMRG with a single matrix product state might fail. You also don't have any obvious structure in terms of UHF orbital bases or any sort of translational symmetries that you can easily exploit. So this is much more of a black box method, whereas with the NOQE, you really needed to know a lot about the sort of qualitative structure of the wave function in advance. Here, you can just add matrix product states one at a time to iteratively construct your subspace. So I would love to go into more detail about how the hybrid quantum classical optimization of this works, but I am pressed for time, so I'll just say that it has some attractive features, such as avoiding the need for gradient-based optimization, and you can also get very well-conditioned overlap matrices this way. Okay, so just to reiterate that the sort of key source of quantum advantage here is in the computing the off-diagonal matrix elements to some constant or inverse polynomial additive error. So there's no known classical algorithm to do this. With a quantum computer, you can map these matrix product states to staircase-like quantum circuits, And this means that you can, you can use a linear depth Hadamard test circuit to find these using a quantum computer. We also tested this method out on, so here a stretched water molecule and an octahedral arrangement of 6 hydrogen atoms. And we found that we could achieve reliable convergence with a smaller number of tensor parameters than DMRG or comparable other sort of classically tractable analogs of TNQE. We also showed that the we can we also showed that so for molecular systems that have a lot of static correlation, we have much more reliable convergence than methods such as VQE with a UCCSD reference state, with much shorter circuits. And as we scale up to, if we think about adding larger numbers of hydrogen atoms, we can get better performance. So we show better performance for this small test system, and then as we scale up the size of the size of the system, we can project what the numbers of gates we would need, and we see that we can have orders of magnitude fewer gates per circuit because the scaling is much more favorable. It's a linear depth circuit. Okay, so this is the complexity theory part of the talk. I think I'm probably quite pressed for time, but I will try to cover the main results. All right, so just a brief note. When I talk about complexity grouping problems into so making sort of hardness statements, for any complexity theorists in the room, I am going to use a slightly looser application which allows for polynomial time Turing reductions. So I will say that some problem A is hard for some class like NP. If A is like a function estimation problem or something like that, if an efficient oracle for A would also let you solve an NP-complete decision problem under polynomial time under polynomial time reductions. So just to reiterate our main question here, can we find a useful quantum ansatz for which expectation estimation up to a constant additive error has a provable barrier to dequantization under some complexity theoretic assumptions? And the first thing that I will point out is that you might wonder if finding the expectation values of local fermionic observables could be somehow easier than computing the overlaps between all of these reference states. In other words, could there be some alternative algorithm that means that expectation estimation is in an easier complexity class than overlap estimation? And it's very straightforward to show that this can't be the case. So we show that the overlaps, the overlap estimation task for this multi-reference ansatz is polynomial time Turing reducible to the expectation estimation task. So what this means is that if we figure out something about the complexity of the expectation estimation, if we figure out something about the, if we can prove a sort of hardness statement for the overlaps, it immediately follows for the expectation values too. So now we're sort of honed in on trying to understand how difficult is it to dequantize these overlap matrix elements between correlated reference states. So in the case of TNQE, we have these sort of tensor networks where we have a matrix product state on either side, and then we have this. So this is a particle number conserving matchgate circuit in the middle here, and this always factorizes into linear depth, and we can state this with this lemma here, which is put together from these works on matchgate complexity and free fermion evolution, and this work here on factorizing orbital rotations into sequences of Givens rotation gates. So I'll maybe skip over some of the details here, just showing what these match gates look like, and these are some examples of particle number conserving match gates. So the fermionic swap gate is one. We can also fully characterize these particle number conserving match gate circuits with just two types of gate: these Givens rotation gates and these phase rotation gates. So this is a very dense slide. This is just to situate our results relative to previous work in matchgate complexity. Basically, what we're going to do, thank you. But basically, what we are going to do is to extend prior results to the case of particle number conservation, which is relevant to quantum chemistry. So first, we prove that any logical quantum circuit of can be encoded within a larger circuit consisting only of particle number conserving match gates and controlled Z gates with polynomial overhead in the numbers of qubits and gates. And it's that part about polynomial overhead that is very important here. So we achieve this with a dual rail encoding where we map different logical basis states to so each logical qubit gets mapped to two physical qubits, where the 0 and 1 states map to the 0, 1 and 1, 0 states respectively. So then we can implement arbitrary 1 and 2 qubit gates using only particle number conserving match gates, and for each 2 qubit gate we need at most 3 controlled Z gates. This it's very important that this CZ gate is not a match gate. That's how we can have universal quantum computation. And so with a little bit of extra work, this gives us corollary 4, which states that nearest neighbor Givens and phase rotation gates plus controlled Z gates are a universal gate set for quantum chemistry, which means that any state in the Fock space of fixed particle number can be prepared with just this gate set. And then we also have corollary 5, which is that any logical computation can be encoded by a particle number conserving fermionic circuit, which consists of only particle number conserving match gates, and this if we sort of equate this CZ gate to a double number excitation under the Jordan-Wigner transformation, then we see that this polynomial depth circuit family just corresponds to a sort of generalization of UCCSD, where we have one and two particle excitation gates. So from this follows this further corollary that computing the output probabilities of these quantum circuits up to some constant additive error is BQP-complete. Now this on its own is not too surprising. It's just extending previous results that we had for the non-particle number conserving case to the case of conserved particle number, which is relevant to quantum chemistry circuits. So we also want to know about the more restricted case where we have circuits prepared in linear depth. So these aren't necessarily going to be universal quantum circuits, but can we say anything about the can we make any sort of complexity theoretic statements here? And to gain a better understanding of these cases, we also proved that the controlled Z-gate can be implemented under post-selection using only particle number conserving match gates and a 4-qubit 2-particle fermionic magic state. So this magic state, the important feature here is that it cannot be prepared by any match gate circuit. It could be prepared by a two-body excitation followed by some match gates. So this gives us our main result, theorem 8, which is that orbital rotation circuits with these 4-qubit fermionic magic state inputs is universal for quantum computation under post-selection. And if we then apply known results for these UUPS circuits, we get these following hardness results. So the main one that I want to draw your attention to here is this corollary 10. If this orbital rotation circuit with magic state inputs can be efficiently sampled in the computational basis by a randomized classical algorithm, we call this weak simulation, then we have a polynomial hierarchy collapse to the 3rd level. And for those who haven't seen this before, the polynomial hierarchy is basically an extension of the classes P and NP using NP oracles. And the conjecture that this hierarchy of classes doesn't collapse to any finite level is known as the generalized P versus NP conjecture. So under this generalized P versus NP conjecture, we can now rule out any known dequantization scheme for these off-diagonal matrix elements. We can rule out, for instance, anything based on mid-circuit L2 norm sampling. And I won't go into it for time, but there are also indications of average case hardness in this task. So the case is even more clear-cut when we apply this to NOQE. If we allow for a straightforward generalization of the reference states, then we have that computing the expectation values of local fermionic observables up to some constant additive error is BQP-complete. All right, so I won't cover this slide, but I'll maybe leave it for you to sort of chew on while you think of questions, if we have any time for questions. Okay, and with that, thank you very much for your attention, and I'll be happy to take any questions.
Great. Thank you so much for the talk. Maybe we can take a quick question or two while the next speaker gets ready. Yeah, maybe I'll take my prerogative with the microphone here to ask one. I'm curious about hardness about the hardness in sort of in practice for problems, not where the task is exactly simulating this quantum algorithm, but where this quantum algorithm appears to be useful in the in a context when classical algorithms fail. Do you have some intuition about, if there will be some practical quantum advantage for these kind of approaches?
Yeah, so I think the best kind of intuition that you can draw right now is the one about, so the fact that to represent the dynamical correlation, you need these two-body excitations, and what we prove with our main results is that so these enable universal extensions to the matchgate set. So if you have any kind of orbital rotations at all going on in your method, and you then also add these two-body excitations, that gives you all the ingredients for universal quantum computation. So whether or not realistic cases will be hard to simulate or not will come down to a case-by-case basis. But basically, what we've shown is that all the ingredients are there in the problem. Yeah.
Okay, really nice. Well, thank you so much for the talk.
Thank you.
Let's thank the speaker one more time. And moving on